Hello dear students, we are studying the chapter Solutions and Qualitative Properties. So in this module, let me take you through the understanding of vapor pressure versus the temperature. So let us go with that. Now we'll see the distribution of molecular speeds in liquid. As I said earlier, it has similarities to that of gases. So let's see that first. Well, liquid also have the random motion like gases, as well as their distribution is similar to that of a velocity distribution of gases. So we have learned that in earlier modules also. And we learned that this is because of the Maxwell's-Boltzmann's distribution, which is nothing but a plot between number of molecules versus the kinetic energy. So if I plot that, let us see what I can see here. Number of molecules versus kinetic energy. Now, at a certain temperature T1, this is how the graph varies. This was a similar graph for gases also. Similarly, if at all I increase the temperature, let me take it to T2 temperature, then the graph will vary in this way. That is, it will slowly, the peak will start coming down and it will start becoming more uniform. So in that case, now what I could suggest here is, let us take a point or kinetic energy after which, let's say, liquid particles are starting to escape. Right. So this is the kinetic energy. What I can call is a minimum kinetic energy required for molecules to escape from the liquid state. So that is what it is. So it is the minimum kinetic energy. Now, if this minimum kinetic energy, if at all being drawn towards that curves, they will start touching at two different points. Then they will generate an area under the curve. So let us see what exactly it represents. So at temperature T1, area under the curve represents the number of particles which are escaping out to the vapor phase. So that yellow colored is the area which shows that at temperature T1, how many number of particles have escaped. Similarly, at temperature T2, you could see this blue color shaded part as well as the yellow color part. Both of them combined are the total number of particles escaping out to the vapor state. So it is very clear that vapor phase molecules are more at higher temperature, right? As we learned this earlier also, as the temperature is increased, vapor pressure will also increase, right? So what does that mean? You can see it evidently here. At temperature T1, the number of molecules escaping are very less, but at temperature T2, you could see number of particles escaping are more. So therefore, what I could conclude here is low temperature is equivalent to say that it is less likely to vaporize. That means it is low vapor pressure, while high temperature, it is equivalent to say more likely to vaporize. Therefore, it is at high vapor pressure. So you can now relate how vapor pressure and temperature are correlated to each other, right? So let us try to derive that. Now we know that vapor pressure will only be defined when vapor liquid equilibrium is existing. So therefore, let me consider that liquid vapor equilibrium is there, where K1 is the equilibrium constant and P1 is the vapor pressure. Now therefore, K1 is the equilibrium constant at temperature T1 and P1 is the vapor pressure of liquid at temperature T2. Now what I can say, according to Van 't Hoff's equation, we can always relate that as log of K2 by K1 is equal to delta H vaporization by 2.303 R into 1 by T1 minus 1 by T2. This is the Van 't Hoff's equation, where delta H vaporization is the enthalpy of vaporization, right? Now observe it carefully. Can we write K1 is equal to P1? Because yes, liquid does not have any vapor content. So therefore, vapor phase as P1. So equilibrium constant K1 will be equal to P1. Similarly, if at temperature T2, I can write K2 is equal to P2. So can I change that log of K2 by K1 as P2 by P1? So in that case, this Van 't Hoff's equation will be converted to Clausius-Clapeyron's equation. So students, that is how we derive what Clausius-Clapeyron's equation, which is a relation between the vapor pressure of the liquid versus the temperature for a volatile solvent. So as we go into the next modules, we will see its applications and more importantly, how it will derive towards us the Raoult's law. Thank you.